In order to gain a deeper understanding of the principles of basic optimization, it is useful to consider some aspects of the problem. First, you need to understand that local maxima is not equal to global maxima. In other words, finding a local maximum does not imply that you have found a global maximum. The following example simply illustrates why. Consider a function that looks like this. In this particular function, both this x and this point x2 are local maxima because the slope, as we have seen, are equal to 0 in both cases, and they also satisfy the second order conditions. However, it's easy to see that in this particular example, only x1 is a global maximum. Remark number 2. Global maxima need not exist. In particular, there may not be a maximum, a global maximum, even if the first order conditions are satisfied at some point. The following example illustrates simply how this may happen. So consider a function that looks like this. In this particular example, this point x star is clearly a local optimum, but since the function keeps increasing ad infinitum over there, it cannot be a global optimum. The next remark illustrates a point that we have already seen, but that is worth repeating, which is that first order conditions are necessary for optimization, but are not sufficient. As a dramatic example of this, consider a function like t of x equals x cubed that basically looks like this. For this function, the slope at 0 is 0, so t prime of 0 is 0, but clearly 0 is neither a local nor a global optimum. Remark 4. You may have wondered if the second order condition will also hold when the second derivative is equal to 0. Unfortunately, this is not a sufficient condition for x to be a maximum. Here is an example of how. Look again at the function x cubed that we studied in the previous case. In this particular case, both t prime of 0 and the second derivative are equal to 0. But as we saw before, x0 is not a local or a global maximum. Remark 5. You may have wondered why we keep emphasizing maximization problems and we have not talked at all about minimization problems. And after all, sometimes we want to minimize the cost of something or find the shortest route to a place, etc. The reason is that both types of problems are intimately linked. In particular, minimizing with respect to x the objective function t is equivalent to maximizing it with respect to x the negative of the function. And this can easily be seen in the following figure. Suppose that we want to minimize a function like this, say, which has its minimum at x star. Well, notice what happens if we multiply the function by -1. It just reflects around the x-axis and we get its mirror image. And clearly, if this point was a minimum of the function t, this point has to be a maximum of the function t. So finding the optimal behavior in both cases can be accomplished by solving a simple and closely related maximization problem. Notice that adding a constant to the objective function does not change the optimal choice or the optimal behavior. What I mean by this is the following. Maximizing with respect to x the function t is equivalent to maximizing with respect to x a function t plus some constant. In other words, adding a constant to the objective function changes the value of the objective function, but not the optimal x at which the maximum is achieved. This is a simple intuition to see why this is the case, which is the following. Suppose that you have a function, let's say like this, a function t that gets its maximum at x star. Think about what a constant does. It basically just shifts the function up chooses a parallel which doesn't change the location of the optimal point.